So how you can use convolutional neural networks for predicting things and stuff. So let me share my screen now. Is my screen visible?
Yes.
Yeah, so today we are going to talk about convolutional neural networks. So what exactly is a convolutional neural network? And here by CNN, it's just an abbreviation. We generally call convolutional neural networks. So all my study neural networks. I guess someone whose mic is on. Panish, if you could mute yourself. If you have any questions, you can ask at the end.
Yes, Bhai, I did not know.
Fine. So you would have learned about neural networks in the last workshop, and you have also had an assignment that has been based upon neural networks. So you worked on neural networks in a way that you had images, but you needed to flatten them, right? Like it was an entire 32 cross 32 cross 3 image, like 32 cross 32 pixels into 3 channels, and you had to just flatten that out into a single array with 1 dimension, and then you needed a neural network of that particular size, right? And that is a normal neural network. But here we have a different type of neural network which is called convolutional neural network, which basically builds upon convolutions. I'll explain what convolutions are in a few minutes. So basically, what exactly can this CNN do? So it can do the exact same things that artificial neural networks can do: classification, regression. But apart from that, it can do multiple more things like object detection or face recognition. So if I have an image or a video in which I want to detect the number of people, or I want to detect where exactly are the cars in an image, or for example, in your mobile phones, when you have your screen lock, you can enable face recognition to basically automatically unlock your screen or unlock your mobile, right? So that kind of technology, involves some kind of machine learning, deep learning models, and the exact thing that is used is convolutional networks. So these are the basis of every like computer vision model that is being used right now. Obviously, the algorithms might change in the sense that loss functions might differ or something else, but the main idea remains convolutional networks. So as I explained, like we can use artificial neural networks on images, but we tend to use convolutional networks because in ANNs, as you can see here, for example, this is an image 3 cross 3, right? So I need to flatten it out, and then I use a neural network. And say, for example, I have a very big image, 1000 cross 1000 cross 3. This would end up in a very large number of features. Like I would have so many features, and then my neural network size will also be very big. And if my neural network size is big, weight matrices are very large, right? And if these weight matrices, that wx plus b, if that w is very large in size, then obviously computing the gradient for each weight will take more time, and it basically will result in higher computational time. So that is why ENN is not generally used for images, because it can take a much more amount of time because of the number of features. Also, you know that neural networks are used to detect patterns. Like the initial example that you would have studied across is like in general in machine learning, predicting the price of a house. So finding out the pattern with which the price of a house changes. So neural networks also do the same. But the thing is, like in an image, there might be similar patterns. Like if, for example, we are seeing a human face, so an eye basically has the exact same features. Two eyes of a person have the exact same features, and these are the exact same patterns. So, like it is sort of baseless to basically have two different feature extractors, or having to learn weights which extract patterns from one eye and patterns from the other eye, right? So that actually is a problem. So what we can do is we can have some sort of neural network which learns how to extract an eye from a human face and then use that to extract the same kind of features of the eye in another part of the image, right? Like, or for example, let us say I understand how to detect a car in a particular uh, image, and then I want to detect the same car or a similar type of car in another part of an image, right? So uh, I need something which can basically share parameters or share that pattern detection, right, across the image. Or let us say I want to detect something as simple as a line, and a vertical line, a horizontal line, and there can be multiple lines, vertical, horizontal, etc., in an image. So if I want to basically capture that pattern, I want to have something which can do it across the image without having to learn separately for each line, right? So that exactly is what it is. Convolutional networks are based upon. We need to learn parameters that can be shared across an image. So this is actually what a convolution is, and this is a basic building block of a convolutional neural network. So you can see here that this is an image. The blue area, the blue square is an image, and the output which is being presented here, that is the white square, is the output. So how's it working? So you can see here that there is a 3x3 box which is sliding over the entire image one by one. Like initially it starts at the top corner, then it moves one to the right, then it moves again to the right. Then once it has completely moved to the top right corner, then it moves to the next row, and so on. So what it does is here, it basically slides over this entire image one by one, and then it processes it. So how does it process it? So before that, yeah, before that, we have some important terminology. So this is the image. The blue thing is the image. The kernel. So the kernel is basically that's this small dark blue square that I'm moving over the entire image. This is called the kernel, and these are like this is something that we learn. So you learned about weight matrices, right? So exactly the same thing, just in a different format. Like you need to learn the values of these kernel in order to get some output. So you have some kernel matrix and you apply this kernel to this image and you get some output, and you need to understand what exactly kernel this is, and so that I get the desired output. Right. So moving this kernel over the image is called convolution. Fine. So these are a few important terminologies that you might need to understand. So this is exactly the convolution operation as explained in the previous thing. Now see here, this is an image. The first thing is an image. The second thing is a kernel, and I try to convolve it over the entire image. So if you see, if I overlap it with the top left corner, right? So what I need to do is whenever I overlap it with something, I need to just multiply it with its corresponding values. Like जो भी उसके ऊपर होगा ना, whatever will be directly above that particular value. Like whatever two numbers will be overlapping, you just need to multiply them, and then add all the things in that particular square. So for example, let us say I am at this particular square, right? I want to get the output for this particular square. So I convolve it with this kernel. Now if you see 2 into 1, like 2 and 1 are directly overlapping, so 2 into 1 is 2, then 5 into 1 is 5, 3 into 1 is 3, then I multiply 3 with 0, so this is basically 0, all of these things, and then 3, 8, 8. So all of these are multiplied by minus 1. So you can see here I have, like, this is the result. So basically this is called the convolution operation, where you just overlap the kernel with the image and then compute this, like, sum of products, basically sum of products of overlapping numbers. And if you see here, 2 into 1 is 2, 5 into 1 is 5, 3. So in plus you get around 10, and then approximately you get minus 19 in negative. So minus 9 is the output. And whatever you get here, you basically add that into your output. You can see here initially the 6 I would have gotten from this top left corner. Then I moved 1 to the right. So whatever I got from convolving this kernel, I got here minus 9. And then I move on to this part, then I will get something here. And when I do this, I will keep on getting some values. So some of you might have questions like, why do we not go beyond this? Like, we have just 3 columns, but why don't we go beyond this? Like we could have basically half overlapping thing, like right, half of this thing overlaps with these 2 columns, and the other part -1 doesn't overlap with anything. So that also part we explain it to you in the upcoming slides. But this is the main idea behind convolution. So if anyone has any questions, feel free to ask right now. I'm giving it a pause. So are there any questions or any questions in the chat? Fine. If there aren't any questions, I can move on to the next part. So yeah, you all know about images. Like images are represented as 3D matrix of numbers, right? So 3D matrix, you mean a three-dimensional array, and the first and second dimensions are basically spatial dimension. Like what is inside an image. Like there might be a 24 cross 24 image, and at every pixel you have some value, right? But the third dimension refers to the channel, and the channel is basically what color is it depicting. It can be red, green, blue, and combination of all these channels gives us an image, right? So yeah, this is something that you need to think about. So because you see here, this was a 2D image that I showed the operation upon. But in reality, you will always get 3D images, right? So how do you apply this kernel on those kind of 3D images? So yeah, I'll explain that in a few slides. So yeah, so think of now you can think of convolutions as sort of feature extractors. So this is vertical edge detection. So if, for example, I want to detect vertical edges in, for example, an image. So let us say I have this sort of matrix where on one side all the values are 10 and on the other side all the values are 0. And by 10 and 0, I mean the intensity of the values, of the color values. So you can see that the 0 will correspond to some black or grayish side, and 10 basically correspond to some whiter offset. So now if I convolve it with this filter 1 1 0 0 0 and -1 1, so what this does is basically gives this as output. So you can see here that on the left hand side, because all of the values are same, so this column, the +1 column and the -1 column will cancel out. Same is the case with on the complete right hand side. But if I do something like on this, like on the middle columns basically, so I get 30 30 30. So you can see here that the left the and the leftmost and the rightmost columns are basically black or grayish, you can say. So they won't have any intensity value. But in the middle you have this white sort of thing which has occurred, and this shows that okay, there was I used this kind of filter and there was some sort of vertical edge. That is why this part is showing that there is some white thing and there is this vertical edge. And you see, so this is some sort of an example where you can use a kernel for detecting features, and in particular this kernel, like this particular kernel 1 1 0 0 0 -1 -1 -1 is used for detecting vertical edges, right? So is there anyone who can explain to me, like, or tell me what kernel will be used for horizontal edge detection in place of this vertical edge detection? What kind of kernel we can use? Anyone? Like you can write it in the chat as well. The horizontal for horizontal edge detection transpose. Yeah, so exactly transpose ही use होगा, क्योंकि you can think of it as now instead of, so this was a vertical, so you can see here that ये vertical edge के लिए हुआ था. So now if I wanted to do a horizontal edge, I would just need to transpose this kernel. Now for example, I wanted to detect one vertical feature as well as a horizontal feature. So abhi to we saw that we can use vertical edge detection, this kernel, to get vertical edges, extract vertical edges from the image. But what if I wanted to extract both vertical and horizontal? And exactly, मतलब जब when you work on images, you just don't want one particular feature, you want multiple features. कि भाई मैं एक I have an image and I want to extract hundreds of features, different types of features. I might want to extract vertical edges, horizontal edges, curved edges, or maybe sharp points, etc. etc. बहुत सारे different types of edges I might want to extract, or features I might want to extract. So what I do is basically I have this one filter, right? And I have this other filter. I apply this on the image, ठीक है? I get one output. जैसे यहाँ पे I got an output. The same way for both of them, I get different outputs, and I just concatenate them. तो यहाँ पे 4x4 आया था. Here also I got a 4x4, and I just concatenated them. So I got 4x4x2. So now, initially the number of input channels was 3. The output is 2. Now, what does this output 2 mean? Matlab, I tried to extract two features. Let us say you created 10 different filters, right? 10 different kernels basically. Then this output will be 10. And what will it represent? Ki you try to extract 10 different types of features from your image. Okay? So that is the main idea. Now I come to the point where you see this is 6x6x3 image, right? Like we want to work on images which are multi-dimensional, जिसमें 3 channel हो. So how do we do that? And even like अगर मेरे को for example I applied convolution on this, and then I wanted to apply convolution on this. So this could have 10 channels, right? So I need to understand a way that I can apply convolutions on such a 3D image. So yeah, so this is exactly the way you do it. So अभी मैंने देखा था जैसे you used to overlap on one particular channel, right? Yeah, one particular thing. Now what you do is you use that particular kernel, like whatever kernel you are using, you just replicate it कि मैं पीछे भी same values डाल दूँ, ठीक है? Like -1 वाला जो अगर kernel है, if I have this here, then I just copy it to the other channels here, and then I shift this cube basically across this entire channel, ठीक है? So across this entire like cube. So initially I had a 6x6x3, ठीक है? और फिर इसको I overlap it, and then I do the same thing. जो भी overlapping numbers हैं, I multiply them and then I add them up. Similarly, I shift it one side, then I shift it one column, and then so on. And similarly, I shift it across rows. So that is the main idea behind convolutions. So for example, let us say यहाँ पे if there would have been 3, instead of 3 there would have been 10. So यहाँ पे my kernel size would have been 3x3x10, and then वो मैं basically convolve कर लेता हूँ, right? But let us say so, and this basically will give us a 4x4 image. And अब इसका जो ये क्योंकि मैंने सिर्फ I used only a single filter, that is why it was 4x4. If I had used multiple filters, then I would have gotten 4x4 plus number of filters basically. Okay, so this is basically whatever I've explained till now is 2D convolutions. Fine. So 2D convolutions are these. 1D convolutions you don't need to understand right now, but if you want, you can go through that particular part. Basically, instead of having this 2D kernel, उसमें सिर्फ 1D kernel होगा, like one dimensional instead of this 2D array. ठीक है? And 3D convolutions. तो 3D convolutions में you can see here जैसे अभी यहाँ पे I had this 2D image, like 2D kernel, and I just had the same values in each of the three things, right? But let us say, and the number of filters, yeah, this 3 is equal to the number of channels. अगर यहाँ पे 10 होते, so this would have been 10. But 3D convolution is used in separate ways. So if I want to have, say for example, across different channels also, I want to extract different features, different types of features. So that can be also used कि यहाँ पे I have some other filter, उसके पीछे I have some other type of filter values, and behind that also I have some other type of values or features. Okay, so that kind of thing is convolution, 3D convolutions. But we generally don't work with 3D convolutions. We generally work with 3D convolutions in case of videos and stuff. If you have a video, then we work with 3D convolutions. But in general, if you have images and stuff, you can work with 2D convolutions, and they work pretty well. Now moving on to padding. So these are a few important things which might help you in increasing your accuracy and stuff. So what happens sometimes is, like, as I use a convolution, it decreases the size of the image, right? From 6x6 it went to 4x4. Now as I keep on increasing the number of convolution layers, right, the image size will keep on shrinking. Okay? And if I use, for example, 5-6 convolutions, then the image size can pretty much decrease a lot. So that is a problem with convolutions. Apart from this, corner pixels, like the ones on the top corners or the bottom corners, these are used only once, like only on the top left, only this particular 4x4 mein, only this particular pixel corresponds to this pixel, the top left. Same is the case with the top right, bottom right, top left. But if you see in the middle, like for example this pixel will come in like every sort of like multiple pixels in the output. So think of it as I'm giving more importance to the pixels in the center than at the borders, kind of that. So that is what happens with convolutions, but that might not be a very good idea. Like there might be important information in the edges or the borders which might be helpful. So what we do is we pad the image to get a bigger image as output. So think of it as मेरे पास this was the image. Now what I can do is I can add a bunch of zeros here, right? And then I can use a filter and kernel. So you can see here that अब I had a 5x5 image, ठीक है? I used the 3x3 kernel or filter and I got a 5x5 as output. So this is what exactly padding does. It helps you in increasing the size, and sometimes it also helps in giving importance to the features on the corners. Now there can be different types of paddings. It is not necessary that you just use the zero padding. You can have maybe one padding or maybe some. So there are different types of paddings. You can Google them. So different ways in which you can pad your images. Now strided convolutions. So what exactly do strided convolutions do are like in now instead of shifting it one by one, like initially what I did was I shifted the kernel one by one, like this was on the top left, then it would shift by one, then it would shift by one, right? Instead of that I can shift it by two as well. So this sometimes helps if you want to downsample, like converting a small bigger image into a smaller image is called downsample. So if you want to downsample at a faster rate, like if you want to decrease the size at a faster rate, you can use strided convolutions, and this helps in some cases, but generally we keep it to one, and this might also help in decreasing the computational time. So that is why it might be used sometimes. Then max pooling layer. So this was all about convolutional layers. Like these are the basic fundamentals behind convolutional neural networks. Now, like we'll be moving on to some kind of layers which are generally not used in neural networks, artificial neural networks, but they are used in convolutional neural networks. So this is a max pooling layer. So you can see that this is a 4x4 image, and if I use a 2x2 max pool, so max pool what it does is it takes a square like a two. If I specify it to take a 2x2 image, 2x2 square, so it will take this 2x2 square and find the maximum value. So this is 20. Here also, if I find the maximum value, this is 30, this is 112, and this is 37. Okay, so can anybody tell me what exactly is the stride? Like I explained here that stride is basically you can shift one, twice, thrice, okay, as many times as possible. So what is the stride for this max pooling layer? If anybody can uh, tell in the chat. Like anybody, two, fine. So exactly, so the stride is 2. Yeah, so the stride is 2 because you see, if it had been 1, then it would have focused on this 20, 30, 12, and 12 wala square, and it would have created the max out of that as well. Then moving on to average pooling. So the same thing. Instead of taking the max, I take the average. So 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 9 is 17. 17 divided by 4 is 4.25. So that is what it does. It takes the average across each square. But how exactly do you use this stuff? So you just need to add these convolutional layers to your neural network. Like you can see here, you have an input. So now, as you were working with images in your last assignment, you had to flatten your images. Instead, you can just use them as they are 28 plus 28 plus 1. You have a convolutional layer, right? And then you have this number of filters, like you have a number of filters, so it gives you n1 channels. Then you have max pooling. So max pooling won't decrease your channels. It does, what it does is it just takes the max across each channel. So max, like it does max pooling across all channels. So that is the thing. Then you have another convolutional layer, you apply that, you have another max pooling layer, and then what you can do is you can flatten your whatever output you have here, or even if you don't want to, you might not even want to flatten it, that is up to you. So you can flatten it, then you can use a simple neural network. So that exactly how convolutional networks work. But enough of theory. So I guess we can now move on to the implementation side, where we'll be talking about how you can add them to your convolutional neural networks, how you can add convolutional layers to your neural networks. So I guess this was your assignment, right? So I won't be going through the entire thing. Yeah. So you can see here that this was sort of an artificial neural network model which could be built, right? But now I'll be focusing on CNN model. So now we have a CNN model where you have the first layer which is self.cnn. This is my first convolutional layer, right? And we import, like this is a convolutional layer that is there in PyTorch conv2d, which means 2D convolutions. And in there we have in channels equal to 3. So in channels means that you have an RGB image and the number of input channels that are going to come. So if for example you have a black and white image which has only one image, one channel, then this would be basically 1. Now that we have an RGB image, we can write it out as 3. Then we have out channels. So basically out channels defines the number of channels you want in the output. And by this, what I mean is the number of filters. As I said in convolutions, the number of filters you have, the number of different filters you have. Yeah. Does anybody have a question? Right. So the number of filters you have is basically equal to the number of out channels, and so that is why we have kept it as 16. You can have it as much as you want. Then you have a kernel size. So generally kernel size is preferred to be 3 or 5. So you can have that kernel whatever you want. And if you want, for example, you can even change the kernel size like 3 cross 2, I guess. Yeah. Want, you can have different kernel sizes for X and Y. Like if you want a 2 cross 3 or a 3 cross 2 kernel, you can have that as well. Then you can have the stride as well, like uh, stride if you want to have 1 or 2 or 3, whatever you want, you can have that. And then this is the padding. Padding equal to 0 means no padding. Fine. So this is a convolutional layer and then a max pool layer. So the max pool layer is this, and this is kernel size equal to 2, like a simple kernel with size equal to 2. Right. So that exactly what we have done. This is another convolutional layer, 16 in channels. If you see here, the out channels here were 16. So here the input number of channels will be 16. Out channels, if I want 32, then it's 32. And then you see we have a fully connected layer, which
भैया बाय डिफॉल्ट पैडिंग किस पे सेट होता है?
पैडिंग 0 पे सेट होता है बाय डिफॉल्ट.
ओके थैंक यू.
और फिर जैसे ये देखो कि लाइक आई हैव दिस फाइनल आउटपुट, ठीक है, मैक्स पूल के बाद, एंड देन आई क्रिएट अ लीनियर वाला लेयर. एंड इफ यू सीन फॉरवर्ड वाला फंक्शन आई हैव डन सेल्फ डॉट सी एन एन के थ्रू जा रहा है, देन रीलू मैक्स पूल सी एन एन रीलू मैक्स पूल, एंड देन व्हाट आई हैव डन इज फ्लैटन इट आउट. मतलब कि जो भी हमारा आउटपुट आया था, वॉट एवर आउटपुट आई गॉट फ्रॉम दिस मैक्स पूल लेयर, I flattened it out into a single array for each value. ठीक है? So that exactly is the thing. And then I use this self dot fully connected layer. So you would be thinking like, how did I come up with this 1152 वाला thing? ठीक है? Output तो was 10, वो तो नहीं, but वो दिक्कत नहीं, but 1152, how did I come about it? So you initially had a 32 cross 32 cross 3 image. ठीक है? Now fine. So I have a 32 cross 3 image, right? And then what I do is I apply convolutional 2D layer on this. ठीक है. So अगर तुम देखोगे, so it decreases in size, right? So how does it decrease in size? 32. It does. मान लो you had a 6x6 image and उसमें से 3x3 हटा रहे थे कर्नल. You used a 3x3 कर्नल. तो आउटपुट क्या आ रहा था? 4x4 आ रहा था ना. So if you think logically, तो उसमें अगर you have an n मतलब n cross n image, ठीक है, and you use this sort of thing like minus f, like filter size अगर 3 है तो minus f होगा, like 32 minus 3, बट उसमें एक प्लस वन भी होगा, लाइक तुम फॉर्मूला देख सकते हो. एंड स्ट्राइड्स वगैरह के लिए अलग होता है, लाइक बाय एस कर देते हैं. लाइक स्ट्राइड अगर 2 रखेंगे तो ऑब्वियसली और छोटा हो जाएगा, तो बाय एस हो जाता है. ठीक है, लेकिन ये सब मैं अभी फॉर्मूला नहीं बता रहा, तुम लोग खुद से सोच सकते हो वो. बट द आइडियाज ये बाय 2 चेंज हो जाता है, लाइक अगर कर्नल साइज 3 हुआ तो इट डिक्रीज बाय 2. ठीक है, देन द आउट एंड द नंबर ऑफ चैनल्स इंक्रीज टू 16. देन आई यूज्ड मैक्स पूल. ठीक है, सो मैक्स पूल से हाफ हो गया साइज, बिकॉज हर 2x2 पे हम वर्क कर रहे थे, तो 15x15 हो गया, क्रॉस 16. एंड देन 13x32 हो गया, बिकॉज एक और कॉन्वोल्यूशन लगाया. देन अगेन मैक्स पूल की वजह से हाफ हो गया. ठीक है, 6x6 हो गया. एंड देन ये वैल्यू बेसिकली बराबर आती है. ठीक है, सो ये है बेसिक कॉन्वोल्यूशनल न्यूरल नेटवर्क, एंड यू कैन यूज दिस फॉर वॉट एवर लाइक images you want to work on. ठीक है, so I guess that was the main idea behind convolutional networks. अगर किसी को like if anyone has a doubt you can ask right now. ठीक है, if no one has a doubt then yeah, Rishabh Pyle, you can start with OpenCV.
Yeah. Yeah, okay. Is my screen visible?
Yeah.
Okay. So now you people have learned about computer vision and CNNs. I will be introducing you to another interesting topic, which is image processing and a library, OpenCV, that will help us carry out this image processing task. So I think all of you have used Instagram or Snapchat filters. Like so, these filters are also enabled through image processing. Like sometimes people get confused between computer vision and image processing, and they use these terms interchangeably, but they are not the same. Computer vision actually enables computers to recognize, interpret, and process the images as we human can do. Like we can distinguish between objects, classify them, and so forth. But and for this it uses several techniques, and image processing is one of them actually. Like image processing is actually simply means that we use some algorithms that does some transformations on images, such as smoothing, sharpening, or stretching the image in order to get some useful information from it. So it's kind of image manipulation. And for that we use OpenCV. Like OpenCV is actually an open source library for image processing, which has more than 1,000 algorithms to perform all these tasks, so that in order to get desired outputs. And some people also use machine learning for image processing, but it it is a OpenCV is actually very handy tool when it comes to image processing. So it's very important for us to learn about it, because many times we have to pre-process the image before we actually feed it to the our main computer vision model. So yeah, this is all about what is image processing. And now I will be starting with the basics of OpenCV. So first of all, let's start with the installation. Like OpenCV can be installed on any operating system. It doesn't have any uh, specific requirement for that. Like for it can be installed on Linux, Windows, and Mac OS. For Windows, we have to simply write this command in the command prompt. Like here you can see. So you just simply have to write this command here. Like it's showing the requirement is already satisfied because I have already installed it. So this is how you install the OpenCV with the help of pig package. And to check whether it is installed properly or not, we just simply import the CV2 library. Like if it doesn't give an error, we like that CV2 is installed properly. Okay. Now, before performing any transformation on images, we first of all we have to know how to read the image. So for that, OpenCV provides a function called imread, which has two arguments. First one is the path, which is image path, and the second argument is flag. So flag actually specifies the way in which image should be read. So it can have three values. The first one is imread color, second one is imread grayscale, and the third one is imread unchanged. So like instead of writing these values, we can simply write the numbers corresponding to it. So the in first method, it specifies to load the colored image. The grayscale one specifies to load the image in grayscale mode, and the third one specifies to load image in including the alpha channel. So alpha channel is actually a channel that handles transparency, or you can adjust opacity of that image with the help of alpha channel. Okay, and to display the read to display the image, we can use cv2.inshow, where the first argument is the name of window and the second argument is the image that we want to display. Here you can see I have used cv2 wait key, which actually holds the popped up window for defined time. Like the time is specified in this parenthesis, and which is it's actually in milliseconds. And if you want to hold the window for an infinite time, like until you press any key, you can simply pass a value 0, or you can keep that parenthesis empty for that. And the all window will destroy, like close all windows after we have performed our task, like here. So this is the image that I have read using imread and displayed using imshow. And after pressing any key on keyboard, it will simply close the window. Okay. Now, the next thing is if you want to save an image, you can do it with a method called cv2 imwrite, where the first argument is the path for image. While writing the path, you also have to define, like specify the format in which you want to save the image. And the second argument is the image. Okay. So it will simply return true if image is saved successfully. Like here it has returned to true. So now I will try to read that image once again. It has saved the image with name dog.jpg. Okay. Now, so for resizing, many times we have to resize the image before we pass it to our model. Like basically, we will use the resize method for scaling our image. So it helps in reducing pixels in image, which is also useful in reducing the training time of a neural network. And we can also use this function for zooming out the image. So here OpenCV has this method called CV2 resize for it, and it has we have to pass three arguments. The first one is image that we want to resize. The second one is the dimension to which we want to resize the image. Okay, like here I have actually, suppose I want to reduce the size of image to half, then what I will do is I will simply multiply the original dimensions with the scaling factor I want. And one thing here to note is that this value should always be in integer. Like that's why I have written here int. Otherwise, it will give an error. And the third argument is interpolation method. So if you want to shrink the image, we can use the CV2 inter area. The second method, intercubic, is more efficient, but it's actually slow. And if you want to zoom out the image, then we can use the third interpolation method, which is interlinear. Okay, so here you can see the output. Like it has reduced the size to half. Okay, and if you want to zoom out, then you can simply change the scaling factor here. Yeah, it has increased the size. Okay, is there any problem? Like if you have any doubt, you can just simply unmute yourself and ask me. Okay. So now the third one is how we can rotate the image using CV2. Like for rotating image, we first have to define a specific rotation matrix or transformation matrix. That matrix is usually of the form as shown in this figure, like as shown in this figure. And OpenCV actually provides us a ability to define the center of rotation and also the scaling factor for the image, like how we want your output image to be. After a modification, like using center and the scaling factor, we get our matrix something like this, where alpha is the scaling factor into cos theta term and beta is the scaling factor into sin theta term. So here OpenCV provides a method called get rotation matrix 2D for specifying the rotation matrix for it, where it takes three arguments. The center of rotation, here I have assigned the center of image for as a rotation center, okay? And the angle which you want to rotate image in anti-clockwise direction. Like if the angle value is positive, the image will be rotated in anti-clockwise direction, and if it's negative, it will be rotated in negative, sorry, clockwise direction. And the third one is the scaling factor for the image. Like if you want to preserve the size of image, you can simply pass 1 here, okay? And this warp affine function will simply do the appropriate shifting required using that rotation matrix. So here, if I run this cell, here you can see that it has rotated the image in 45-degree anti-clockwise direction. If I change it to negative angle, it will simply rotate it in clockwise direction. Okay, so this is about rotation. And now simply like we can draw various types of shape on the image. Sometimes we need some shapes to highlight any object in that image. Okay, so for that we have several functions in OpenCV. The first one is CV2 dot line. Like if you want to draw a line on image, you can simply use this function, which has 4 arguments. The first one is the original image on which you want to draw the line, the starting point, end point, and color and thickness. One thing here to note is that 0, 0 will represent the top left of image. Like you can simply treat it as standard Cartesian coordinate system. Okay, so here you can see the output. Like color specified is in BGR scheme. Okay, and the thickness is in pixels. So here it has drawn the line on the image. Okay. Now for rectangle, we have CV2 dot rectangle, which also takes the similar arguments. Like here start and end point will be two diagonally opposite points, and thickness is also in pixels. So here it has drawn the rectangle of specified dimensions. And one more thing here is, like, if you change the thickness value to -1, it will actually fill the rectangle with specified color. So it has filled whole rectangle with black. Okay. And for circle, we also have a function called cb2.circle, where it takes the center coordinates and radius of the for that circle. One thing here to note is that, like, wherever I have used int to convert the float value, like that argument should always be an integer. Otherwise, like cb2 will throw an error here. Okay. Also, same thing of thickness. Sorry, thickness apply here. Like, if we change it to -1, it will fill the whole circle with the specified color. And to draw a triangle, we can simply declare 3 points and use line function for it. So yeah, this is about how we can draw several shapes on image. Now coming to the next topic, which is image smoothing. So why we need image smoothing? Like, it is used in image processing to remove some noise which are present in images. Noise as in it removes low intensity edges or smooths the images and sometimes helps hiding some details in the image. So for image smoothing, we have 3 types of algorithms. The first one is Gaussian blur, the next one is median blur, and the third one is bilateral blur. So in various types of noises are due to camera sensor. So Gaussian blur basically eliminates high frequency content such as edges or background noise from the image with the help of Gaussian function. So here CV2 has a method called Gaussian blur for it, which take 3 arguments. Like the first one is image, the kernel size. So the kernel is similar to what you taught in CNNs. Like it's a matrix that the algorithm uses to scan over the whole image. And here the last argument is sigma, which dictates the width of curve in xy direction. So if sigma is set to 0, it will be calculated automatically by the kernel size. So here, like, I will be showing the output of all 3 filters in last. Like, it will be easier for you to compare how these filters works. The next filter is median blur, which is similar to Gaussian blur, but here it takes the median of all pixels present in that kernel area and replace the element, replace that particular central element of uh, the kernel with median value. Okay, so here also it takes 2 arguments, the first one image and the kernel size. And these 2 filters, like Gaussian blur and median, will actually, along with dissolving noise, sometimes will also make the edges disappear. Like, it makes edges very less sharp. So to avoid this problem, we have a filter called bilateral filter, which is an edge preserving and noise reducing filter. So here it takes 4 arguments. The first one is image. D is a filter size, which is also in pixels, and sigma color and sigma space. For simplicity, we can keep these 2 values, like this sigma value, similar. But if they are too small, the filter will not have much effect. Whereas if they are too large, it will have very strong effect, and the image may look much cartoonish. Okay, so we have to choose this value perfectly. So in order to not get such results. So yeah, if I run it. This one is the Gaussian blur. Like, it has blurred edges. You can see. Median blur had also reduced the noise, but it didn't preserve the edge. But if you see the bilateral filtering, it has reduced noise, but also preserve the edges. So these are the 3 filters for use for blurring. So now coming to what is image thresholding. So it image thresholding actually simplifies the visual data for our analysis. So basically, like basically thresholding will convert images into binary format so that we can use it as a way for finding out or to select the area of interest. So in thresholding, actually each pixel value is compared with a specific threshold value, and if it is above the specified threshold value, it will be replaced with a max value, which is usually 255. For threshold, before applying thresholding, actually we have to convert the image to the grayscale format. And note that grayscale also has at least 255 values ranging from 0 to 255. The threshold, like here, there are 2 types of thresholding. The first one is simple thresholding, and then another one is adaptive thresholding. So in simple thresholding, it's actually called binary thresholding also. Here, first of all, I have converted the RGB image into grayscale, and CV2 has function method called CV2 threshold for performing thresholding, which takes 4 arguments. The first one is image on which we want to threshold, and the threshold value, the max value, and thresholding technique. The first technique is thresh binary, in which if the pixel value is greater than the threshold, then it will be set to max value, which is maximum value, which is 255. Like if I run, so here this is the grayscale image. Here I have kept the threshold value as 140. So all the pixels above 140 will be set to max value, which is 255. Therefore, this area is white, as you can see. The next technique is thresh binary inverse, which is exactly opposite of thresh binary. So here you can see if the given the pixel value is greater than threshold, it will be set to 0, and all other values are set to 255. And the third method is thresh trunk, where if the pixel value is greater than thresh value, it will be set to that thresh value, not the max value. So here you can see all these 3 outputs. This is how thresholding works. But suppose if you have an image with a lot of like if you have image with shadows on it, simple thresholding will not work properly because it keeps the threshold value constant throughout the operation. But here you can like suppose if I try to apply simple thresholding on this image, it will give output something like this. Like we have lost a lot of information because the threshold value is constant throughout. But adaptive thresholding actually calculates the threshold value for each region, like each small region. Therefore, it actually it calculates threshold value for each region separately. Therefore, like here you can see the CV2 provides adaptive threshold method for it, which returns the thresholded image. Here the 255 is the max value. It has 2 adaptive methods. The first one is adaptive thresh, mean this method actually specifies how the threshold is calculated. Okay, here we have a block size and a constant. So here for thresh min, actually it will calculate the mean of neighborhood area values of that pixel, and it will subtract a value, constant value, which we have here from that pixel value, and that's how we get the threshold here. And for Gaussian one, we actually have a formula called like Gaussian minus the weighted sum of all the neighborhood area values minus the constant value. So here, if you see these two outputs, so in this one, it has calculated the mean, and in thresh 2, it has calculated the Gaussian value of it. Okay. So now, so this thresholding will actually help us in masking the image. Like masking image actually used for, like it is actually used to get the area of interest for us. Like suppose if there's an image which contain some fruits or vegetables, and we want to crop out the fruits which has red color, then how can you do that? So uh, so this bitwise operation and masking will help us to do that. So first of all, let's see this bitwise operation that we can perform on image. So here, these are the two image I have taken. One thing here to note that like both the images which we are going to use for bitwise operations, we should have same value. Therefore, I have resized the second image to the dimension of first image. So bitwise and is simply similar to the mathematical bitwise and we use. So here we treat black as 0 and white pixels which are 255 as 1. Therefore, after taking bitwise and between these images, it will turn off several pixels, and the result will look something like this. If you take bitwise OR, it will have all the white pixels. Like if you compare these images, after taking a bitwise OR, it will white out the entire image. And a bitwise not will actually invert the bits. Like if it's 1, it will convert to 0. If it's 0, then it will convert to 1. So this is bitwise operations. And the mask will allow you to focus on part which we want to extract. So let's see. Suppose this is a traffic light signal image, and I want to just crop out the red light from it. So how can I do that? So for that, CV2 actually has a function called inrange, which will help us to segment out particular color from image. Like here, we don't have to first for like here for thresholding, we don't have to convert it to grayscale and check the value with hit and trial. Like you can simply use the inrange function, which takes 3 arguments. The first one is the image on which you want to threshold, and 2 other arguments are the color range. Like here, I want to crop out red, so I have written HSV values, HSV values for red color. So like actually, I have converted first of all, I have converted the image to HSV format because HSV is actually robust to external lightning change. Like you can use BGR values also, it doesn't matter. So after applying that threshold, I will get the thresholded image something like this, and I can treat it as a mask. So using bitwise, and I will actually take them and between this mask and the original image. Hence, it will zero out all the bits which are black in the mask. Hence, I will get output something like this. This one is the bitwise AND of the red mask and the original image. So I have I have cropped out the red part, which is okay. So this is about the masking. And for OpenCV, like now let's next topic is OpenCV contours. So contour actually means that um, a curve joining all the continuous points on having the same color. So for finding contours, we actually use the thresholded image. So here, like if I apply the find contour function on this thresholded image, it like here you can see that sorry one second. I don't know why it's happening. Okay. So it will return actually a list of contour points. Like for this image, it actually returns a list of length 11. Like it has 11 contours in it, and each contour will be the set of points. Like and after visualizing it, we can see that like if you draw the contour using draw contour function, it will be something like this. Okay, so here it has also drawn the small contours which are unnecessary. So for removing that, what we can do is we simply run a loop. We simply run a loop where I keep a condition that first of all I will calculate the contour area, and if that area is greater than 100, then only I will draw that contour. So this is how it looks when I remove all unnecessary contours. So this is all about contours. Now Rishabh will continue remaining features of the OpenCV. Okay.
So let me share my screen first. So is my screen visible?
Yeah, it's visible.
So, okay. So hello everyone, my name is Rishavar and I will be continuing to this introduction to OpenCV notebook. And also I want you to know that OpenCV is really a vast field to discuss here. And we cannot discuss everything in just one workshop here. So we are going to just highlight some important and basic operations of OpenCV. And also for your better understanding, we are going to provide you some external resources as well. So basically, when it comes for image pre-processing, we need to process it, clean it before applying any algorithm on it. And if you have a good knowledge of OpenCV tools and function, then it is one beneficial factor to you guys. So coming to this morphological operation, the first question arises in our mind, like why do we need these operations? So the answer is simple. We uses these operations to extract some important components within the image, or sometimes we want to clean up the noises in the image, and that's why we uses these operations. So these morphological operations require two things majorly. First one is your binarized image, and binarized is a thresholded image, and second is your structuring element, that is the kernel, right? So a structuring element is nothing but a box or a window which is going to iterate over the entire image, just like the convolutional, you have seen the convolutional window. Instead of convolutional operations, here we are going to perform bitwise operations. And based on that, we defined several operations like erosion, dilation, opening and closing, and so on. For now, just understand this structuring element is nothing but a window which is going to iterate over the image. So as you can see, when this structuring element is going to iterate over the image, it can possibly end up with three possibilities. This A, B, and C. Sometimes it is going to have entire black pixels. Sometimes it is going to have white pixel and mixed up of sometime. So that window structuring element can have the possibilities, right? So let me first load the image. So here I am reading the image using cv2.imread and then converting into grayscale image, and then finally I am using the thresholding technique to binarizing the image. So after binarizing, we are going to have the image pixel values either 0 or 255. So let me run this cell. So as you can see, this was the original image previously we were having. We then converted it into grayscale image, and then that is the mask or thresholded image we have. Because we want to perform morphological operations, and therefore we need a thresholded or binarized image. Then that's why we have converted it into a thresholded image. So coming to this dilation operation, so like sometimes it happens that we cannot see some minority details in the image, and to see them we do processing using this dilation operation. And in this, our structuring element is iterates over the image, and within the window, if it found at least one white pixel, then the window's pixel will be becoming one, right? In the forming dilated image. For the image, you can see this sort of enlarging the minority details, the small components in the original image. So this is the dilation operation actually. It sort of enlarges the small components, right? So implementation is easy. You first need to define the kernel, that is the window which is going to iterate over the image. And then using this cb2.dilate function, you're going to have the dilation image. So pass this binarized image, then your kernel, the window, and then iterations. So iteration is the number of times you want to perform this dilation operation. And so here it is 1 by default. And if you want to perform multiple times dilation operation, you can put the value here. So let me run this cell. So yes, that was the masked image previously we were having, and this is the dilated image. So as you can see, the small details have been enlarged here. So that is the main work of the dilation process. So here we are going to enlarge small components of the image. So that is what dilation. And erosion is like opposite of this. Here we are going to thinning the image. So here this rule is when all the pixel value of the structuring element, when the structural element is going to iterate over the image is 1, then the value of that particular pixel will be 1. Otherwise it is going to 0. So it's sort of AND operation here. Previously we were having OR operation within the window, and here we are having this AND operation. So it kinds of thins the components of the images. So, and for that, for implementation, syntax is also same as previous one. Just you have to use the kernel one, and then you have to use this function cv2.erode, pass your masked image and kernel and the iteration. Iteration, that is the number of times you want to perform this erosion operation, and then simply run this. You will be seeing previously we have this some noises in the original image, right? So now using erosion operation, we can get rid of that small noises that may be present in our original image. So right. So after that, we were having this opening and closing operations. So opening is nothing but firstly we are going to perform this erosion operation, and then we are going to perform dilation operation on the same image. The result we are getting is this opening image. So also syntax is same as the previous one. Use this cv2.morphx function, and within the function you will be going to pass the binarized image and the method that you want to perform. So here we want to perform opening operation. That's why we have here method is this cv2.morphopen, and then your kernel size. So run the cell. You're going to have this opening operation, right? So closing, another operation is your closing operation. Closing is opposite of opening. It is firstly we are going to perform dilation operation, and then we are going to perform erosion operation. So syntax is also same. Only the method you need to change here, that is cb2.morph close, because we want to perform closing operation. So let's run this cell, and here that is the outcome that we have. So actually there are multiple operations, these morphological operations. So I would suggest you to run various operations and observe which technique or which operation is giving you the results that you want. So basically these operations are used to highlight in some important component or to remove some noises in your original image, right? So coming to this Kenny's detection method, now sometimes it happens you want to detect the edges in the original image, right? So for that you can use this Kenny's detection method, and again there are several of other methods like Laplacian, Sobel X, Sobel Y, Sobel compound. There are a lot of hundreds of methods to detect the edges present in the image. So here I am using Kenny edge detection method because it's sort of a multi-stage algorithm which performs noise reduction, gradient calculation, non-max suppression, and after that it is going to provide you the edges present in the image. So to apply this Kenny edge detection method, firstly you're going to read the image using cv2.imread specified path of the image, and then using the cv2.kenny method, which is going to take argument as your image, original image, and two threshold values. That is the two threshold values between them you want to detect the edges in the image. So that is the syntax for it. You can just run the cell. You can observe these edges. This is the messy. These all ages have been detected here correctly. So because of the Kenny's detection method, we don't have this the people which are sitting in behind the stand behind that. So it performs this noise reduction method, and that's why we have this ages of this only messy only, right? So actually it is a very best method I can say for age detection, this Kenny's detection method. Now coming to this RY part, so sometimes you want to crop some part of the original image, and always remember that you can perform that using this RY method. So for performing it, first you need to read the image, then use the cv2 select ROI, which is a selector which will be present on the image, so that you can select the region of interest that you want. So using this ROI selector, you will be having this top left corner and the bottom right corner of the image, and using mathematics we can just crop out the region of interest that we want, and simply we are going to display it. So that is the original image we have. Let's say we want to crop this portion. So just drag your cursor to the region that you want to crop, and if you're done this, then just press enter. Then you will be having this cropped image, right? So after that, this is shape detection. Again, an easy one. Given multiple shapes in an image, your task is to detect the shapes and label it. So for that, firstly, read the image, convert it into a grayscale image, and then use thresholding to prepare a mask. And after that, run contour detection method. So previously, Payal has told you about the contours. So here we are doing the same. Firstly, detecting all the contours in the image, and then after that, we are going to read every single contour that is present in the original image. So after that, the contours we are going to iterate over the contour, and using this cv2.approx polydp method, we are going to approx the polygonal curves. And in a minute, I will tell you how it all works. So once we have this approximated curves, and these curves are closed, so you can check for the length. If you're having the length as 3, then it will be a rectangle. And if you're having length as 4, then it may be a square or rectangle. So you have to check for the aspect ratio. And if aspect ratio is around nearly 1, so it will be a square, otherwise it is going to have a rectangle. And if the length is very high in numbers, then you can assume it is a circle. So let me first run this cell. So here, these were the shapes previously in the image. So your task is to detect the shapes. So here, as you can see, this is not like a straight line, right? The contours are like one is up and one is down. Like, so what we are doing using poly approx db method, it is going to assume this line is a single line. This is not a different line. So that's why we have to use this approximation method to approximate our curves. So, and then after we are going to, we know that it is a closed curve, so we check for the length, and length is 4, so we have checked for it is whether a square or it's rectangle. So similarly for the circle, so if length of the curves are higher than some a value, then you can assume is a circle. So ideally circle is you can assume infinite number it is made up of infinite number of small straight lines, right? So here using approx polydb method, we are going to approx these curves. So this is how we detect shapes in our images. And after that, we are going to read a video. So reading video is also a simple task. Firstly, you have to use the cv2.video capture, which is going to take you a zero. Zero is for index for your inbuilt camera. So if another camera or you have a camera attached to your computer with a USB port, so this indexing can be vary from one or other, right? So zero is is your inbuilt camera. So you will be using this, and after that running a loop and keep reading the frames, right? So using this cap dot read and using this cb2 dot, I am sure you're going to display that particular frame. So so the program will this while loop will continue to run unless you will press this escape key. So escape value of the escape key is 27, and that's why when we press escape key, the program is going to terminate. So let me run this. So it has opened my webcam, so you can press escape to terminate this program. After that, you are having this reading a video file. It is also a simple task. You just need to put the path where your file is located, and rest is the same as the previous one, like reading the video using camera, reading each frame and displaying it. So here we have keeping a break of 40 milliseconds. So each pixel will be uh, viewed or will be displayed for 40 milliseconds, and after that the loop is going to run, the next frame going to run. So this is the video you can like play here. So these operations on the images, same operation you can apply on the video. Like, so what you have to do is to perform this operation within this loop on each frame. So images operations similarly work here, these video operations. So after that, this is one fun part, and you can easily understand by yourself what the syntax and what the code is working. I have commented out everything like what a particular line of code is doing. So here, let me first run this code. So here it's sort of motion detection, performing motion detection. So what we can do to perform this operation is to read two consecutive frames and take the difference of that frame. And if we found a significant change in the difference of the two frames, then we can put a rectangular box over that. So that's how we detected motion detection, right? So you can just press escape to terminate this program. So it is a simple program. You can understand by yourself. I have all these comments out, right? So that's it for OpenCV. And if you have any doubts, please ask now.
Fine, I guess there aren't any doubts. So we'll be having a quiz right now. So share the link.